Okay, so for problem 10, we have 3 parts. The first part here asks us if we have this one rule. I'm not going to give you the whole thing, you can read it on your own, but basically, if we apply this rule until we can apply it no more, what will that do to a string? So let's take an example of like x, y, y. I don't know, right? Well, we take every yx and let's keep changing them to x, y's. I'll apply it here first. Well, actually, I guess there I could only apply it once. There's no more yx's over here. Let's try it. I think you can see that if I have like, let's try x, right? Here I would apply it in the middle first. So we get y, x, x. And then I could apply it here, and this would give me, you're only supposed to do one at once, but these don't impact each other. Y, x, x. Then I could apply it here, and I would get x, y. I could apply it here, and I would get x, y. And then I could apply it here, and I would get x, y. So this will just sort it by x and y's basically, which you could do yourself. You could figure out yourself by trying it on a few examples of strings of x's and y's. The next problem says, the formal language for this is like if s and t are an input and an output string of this process, how are they related? Well, they have the same numbers of x, the same number of y's, but in the output they are sorted all x's first, all y's following. Now it says make your own sort of system of rules where any string of zeros and ones will output 1, or will finish at 1 if they're an odd number of ones, if odd ones, and 0 if even. Essentially is the gist of this problem. So let's think about some really small cases for this, right? This is a class that deals with recursion a lot. Let's look at our base cases. Always, if you've met me in office hours this semester, I'll tell you, first always think about your base cases, or else it's really hard to do any sort of recursive problem. Here my base cases are probably going to be like, well, if it's 0, I don't want to have a rule because that should just finish and say 0. If it's 1, I'm not going to have any rule. So these are not, I don't need these, but let's start with all the possible 2 digits, right? So 1, 1, 1, 0, 0, 1, 0, 0. Well, this is pretty easy, right? 0, 0 has an even number of 1s, so I want it to go to 0. 0, 1 has an odd number of 1s, so I'll just keep it as a 1. 1, 0 I'll also keep as a 1. Here there's an even number of zeros, so I'll move it to 0. And I think this will work because for any length string, like let's take this one up here, it'll turn this 0, 1 into a 1. It'll turn this 1, 0 into a 1. It'll turn this 1, 1 into a 0. And I'll turn this 0, 1 into a 1. So this takes anything that's 2-digit and makes it 1 digit. These are all the possible 2 digits, so I know everything will go down to 1 digit, and I won't be switching whether the number of 1s is even or odd because none of these rules change whether the number of 1s is even or odd. Okay, I hope that argument made sense to you. If not, just take away the general procedure of we can figure out a lot of these complex seeming problems from really small cases. Now it asks, I think, so we define a decision problem as follows. The input is a writing system and a string, blah, blah, blah. The output is yes if it may yield a 1 in the system, and no if otherwise. So this one's a little tricky to think about. The way I might think about it is like, can we make this problem? How hard can we make it, right? If we are given some random writing system, well, what if this loops, right? Looping is the real thing that makes computability hard. Can we make something like this loop? Well, if we have like a system that says turn 1, 1 into 0, 0 and turn 0, 0 into 1, 1, obviously we could have something loop with an input like 1, 1 or like 0, 0. So we can't have a loop. And we know that based on, there's no restrictions on these rules, these loops can be like as complicated as we want. There's no way to tell whether you're in a loop that will eventually loop back or whether you're actually just in a really long string of sequences that is going to end. So this is not a computable problem. If you want to prove it, that might be a little bit difficult, but my argument would basically be, like, we can be in a loop of unknown size, not knowing if we'll terminate, or we could be in a really long sequence of instructions, and we have no way of distinguishing between the two, so we don't know, or there's no way for us to, this is not a computable problem because, I'll draw a parallel between this and the halting problem, right? We don't know if it'll finish, so we can't output a yes in every single possible case, yes or no in every possible case. Like, I would write that up maybe a little bit clearer if I was taking this test, but I hope the general concept there makes sense to you, that if we can form a loop here that doesn't make it obvious it's in a loop, then we can't answer, this can't be computable. It's a little convoluted. Maybe they explain it better in the practice solutions. This is the last problem, I think. So thanks for watching these final walkthrough videos. I guess this is my last video for 201. I want to thank you for watching again. We're really going to try to get these into other courses. If you want to help out with video production or with recording or with doing transcriptions so that there are audio subtitles for people who might be hard of hearing, reach out to me. I'm happy to, the more people working on this, I think the better they'll be and the more well planned out they'll be, and maybe fewer mistakes will be made. But again, thank you all for watching. Thank you for being in this course and for supporting this channel. And I wish you all the best.